So this is EST 204, Heat System Design, Week 2, Lecture 2. We're talking about principles of energy. We need to understand energy because we're dealing with it, we're paying for it, we're having energy crisis. It's good to hear all about energy, this and energy that. So we want to talk about, I think I understand, what do we mean by energy and what's happening. So the first thing we want to talk about is we understand what is energy. When we say energy, what do we mean by that? What kind of energy are we talking about, and how does it look like around us? What is thermodynamics? What is the first law of thermodynamics, which Raj just told us? It's conservation of energy. Second law of thermodynamics is also very intuitive. I'll talk about it. And latent and sensible heat. Me and Bill gonna talk about this until we go in the face, because it's the principle of heat transfer or conducting heat, and also the principle of refrigeration. Latent heat and sensible heat. If you do the refrigeration cycle, probably you have to understand what is latent and what is sensible. So if we think about it from this verbiage, sensible heat, what kind of heat is that? It's heat you can sense. You can feel it hot, you can feel it cold. You got that, right? What about latent? Hidden. So there is heat, you cannot sense it, you cannot measure it. So what does that mean? If you put a thermometer in a pot of water and the water is boiling, what is the temperature going to be? 212. You're adding heat. You keep adding heat. The fire is going on, but nothing. 212. So what is that? That's latent heat. You're adding temperature until the complete water evaporates, nothing will change. So it's going to be constant at 212. Where is this heat going? It's changing the water to vapor. That's latent heat. It's hitting, heat's been put to change phase, change the material from water to liquid. Make sense? Same thing with ice. If you have a bucket of crushed ice, put a thermometer in it. It's gonna be 0. I'll do this experiment for my class for refrigeration. I bring a bucket of ice, and we'll do the whole experiment. I put a thermometer in it, keep increasing the heat, increasing the temperature, nothing happens, still at 32, until the entire ice melts. Then it starts to increase temperature all the way to 212, then it stays there until we evaporate the entire amount of water, then it starts to increase. So latent is hidden, meaning you cannot measure with a thermometer. Sensible, you can sense it, you can feel it. So those two, they're gonna play a major role in heating and cooling. This is the whole principle of refrigeration, cooling, and also for heating. We'll talk about something called enthalpy. We don't have to worry too much about it, but I have to explain the term so you'll look smart when you go in the field and look at the enthalpy chart. We have something called the psychometric chart. So I don't know if I have it here. It's in the refrigeration book. However, yeah, here it is. So this chart is good for refrigeration. They give it to you at any hardware store. It's called an enthalpy chart. And if you look at it, there is a part that says enthalpy. Nobody knows what it means, but they use the numbers. But you can go and just try to act like you know something. Yeah, I know what enthalpy is. I will explain to you in a very layman term what enthalpy is. It's not bogus. It's not a made-up number. This chart has been used for like tens of years now for refrigeration, and it's a relationship between water, vapor, and the energy in it, and how we measure it. That's called a psychometric chart.
Isn't it used in the more complicated equation of the second law?
Yeah.
Yeah, it is.
Yeah, and then also another picture of it here. Of course, I love the psychometric chart because it has so much information in it, and actually it is in 3D. Anyways, it's very interesting, and it took me 2 days to learn how to say psychometric. So, that was difficult. Instead of analysis. Okay, so this is what we're going to cover in this course. So what is energy? It does not come from nothing. It does not come from nothing. Energy has to come from something. We don't know everything. We don't know. In theory, everything came from one big bang billions of years ago. and it composed the entire universe, and we don't know where it's going. It's a big philosophical question, but we know there's a series of events that happened that day. Scientists can trace whatever we have here on Earth in terms of energy all the way back to the Big Bang. Okay, that's what we think, at least in our minds. I'm sure things are bigger than that. For our intended purposes, it does not come from nothing. It transformed from one form to another until heaven knows where. So it's always changing. Do not vanish. So don't think it vanishes. It went somewhere. And I did the example of throwing something up and down. It did change from one form to another. There are some kind of losses in the in the process, but these are not losses. It's just an energy that we cannot use. Useless energy for us. We don't know where it is. And that's also called entropy. Entropy is the chaos of material and things go into disorder in a way that we cannot measure it. Yeah, it gets really surreal and weird, so we're not going to go there. So, when it vanish, conservation of energy. Let's think about small things. Our car, our boiler, that the boiler has fuel in it, and it should go from one form to another. And we can measure within margin of error how much we're going to get out of it. And again, nothing is completely repeatable. If you're going to go to the nitty-gritty and look very small, you cannot repeat things completely. There's so many variables. Here's another scary example. You know that if you play billiard or pool, you know it's impossible. It's impossible to repeat the same shot again. 100%. You can't control your breathing, your muscles, the environment, the vibration. The table has changed from the first hit. So things do not happen, repeat completely 100%. Everything's always subject to change. So with the boiler, the first year it's going, the first time it fires probably 75%, next time it's 75.5. There's always variation. So depending on how accurate we want to have that variation. And some stuff we cannot really control. There is something in something called isentropic efficiency loss. That's usually in turbines. We just, as scientists and that engineers, decided we don't know what is that. We don't want to spend too much time in it. We just know it's 5%. We're going to just like give that to the devil and do that. You know what I mean? So they have a quantity problem. They don't know what is it. And sometimes if you want to do something, if you want to move on, you gotta like just not think about the nitty-gritty. Don't obsess. So this is the first law of thermodynamics. Thermodynamics from the verbiage, it's movement with heat, and that's what you're doing. Movement with heat. Moving things with heat, the heat of the movement of heat, how does it move from one place to another. It's thermo and dynamics, that's what it means. So energy is neither created or destroyed. We're good with that. That's why if you're trying to lose weight, they always tell you to count calories. Calories is energy. How much energy in the food? Sugar has more energy than carbs. Carbs have, sugar has more energy than carb per weight. Fats have more energy than carb, etc. And this energy is counted. Somebody did the statistics on it, and they tell you, for example, 1 tablespoon of sugar is 30 calories. So, and if you run on the treadmill for 10 minutes, you're going to burn 30 calories. So somebody actually sat down and started to measure things and put a number on it. So the food you eat, you're going to transform into mechanical energy. So you become like a car in a way. Fuel and food is the same way. So you have to balance. They tell you if you want to lose weight, your body on average is 2,000 calories a day. But that depends on your metabolism, etc., etc. If you go see a dietitian, they will tell you this is your metabolism based on your activities. If you want to lose weight, you're going to cut down 500 calories. And 1 pound of fat is 3,500 calories. They got it down to a math, to a science. So we're going to cut down 500, and by the end of the week, you should lose a pound. And it does happen. So that's energy again. Food is energy. Where does the food get the energy from? Plants. Where do plants and animals get food from? The sun. So again, we owe our existence to the sun. Then where does it go? It transforms from one form to another. If I can get you to understand this concept, that will be great. It's just moves from one form to another, from solar to plants to fossil, from us in the car, from chemical energy in the fuel to heat energy in the piston to mechanical energy in the transmission. So it moves from one form to another.
So with the greenhouse gases, why can't we use that to
They're trying. There's a lot of science actually. There are companies that are working on machines that will absorb CO2, make it into fertilizer, and use it into the plant. There are some people doing that now. Actually, some companies actually do produce a lot of carbon dioxide. They're investing in those machines. Okay, we're gonna subsidize whatever we're doing. Leave us alone. They make it into fertilizer. They put it into they solidify it, put it back into the ocean, and what happens?
That's like recycling.
Yeah, yeah, you can. There are very many companies doing those filters, but they cost a lot of money. Again, that's why the idea of the carbon tax. So you have some money so you can build those things, or plant a tree or something, and do that. Again, a lot of companies are trying to get more profits, so they want to invest in that. But some companies actually did that. Tesla Motors have some kind of carbon subsidies things. Some are useful to us and some are not. So I'm saying useful to us, but not probably useful to the earth in general, but some of them are not. We want something that have heat. Heat is useful to us. Mechanical is useful to us. Electrical is useful to us. Some of them are not. Okay. Forms of energy. Okay, I will stop here and give you 2 minutes break to talk about. Yeah.